Very well. Today we look at the last fundamental result in, say, single source, single destination information theory, which also completes the material for the test, the written test next week. And this is source coding. Source coding differs from data compression, although some people talk about lossless source coding to refer to data compression. The main difference is that in source coding, we consider sources that typically admit representation under a fidelity criterion. What is a fidelity criterion? Is some distortion measure that tells how different is the representation with respect to the original source. So we do not need to recover the exact bits of the original source sequence, also because this may not be possible. In some sources, for example, an analog signal like my voice, when it is recorded by a microphone and then it is digitized, of course there is some distortion involved. And this sort of finite representation of analog sources involves some form of distortion. And the goal here is to trade off in an optimal way the rate at which we can represent a source and the distortion that we incur in this representation. So I just mentioned recording and digitizing voice, as well as any other analog signal. It could be an image using a CCD and a digital camera, anything that samples some analog source and creates a quantized, digitized representation is essentially what we call the quantizer. So we talk about quantization. What is quantization? Well, we have, in the simplest possible way, we have a random variable, say real valued, x, according to some probability density px, and a certain range of values, x calligraphic, which may be the whole real line or maybe an interval in the real line. And we have a mapping. In fact, a Q-point scalar quantizer is a mapping that maps x into a discrete set of Q values. And how this mapping works? Well, in general, let me draw a picture. Imagine that we have our x is an interval, so it may be, I don't know, the interval between minus a and plus a. So this is our x, and this is the real line. And we define quantization regions. These quantization regions typically are sub-intervals, but it's not necessarily so. You can define as you like, such that if x generates a value in a given interval, then the function f gives the index of the corresponding interval. So this, for example, this is interval 1, 2, and 3, etc., etc. And so in this case, x generates a point here, and so we output the index number 2. Okay, and x generates a point here, and we will output the index f of x equal to q, where q is a number from 0 to capital Q minus 1. So the quantizer is defined by its decision regions. As I say, generally there are intervals. You may define other type of regions. And there is also a reconstruction function, let's call it g, that maps the indices, so the integer from 0 to q minus 1, to representation points. For example, we may associate to every quantization region a particular representation point, for example, the middle point, but it could be something different, as we will see in a second. Is chosen in a convenient way, such that when we receive index q, g of q is the corresponding representation point, let's call it x hat, sub q is the representation point of the region dq. So in other words, this means that we associate, for example, all the values of the source belonging to a certain region, we compact them into a single representation point. And of course, by doing so, we incur in some sort of distortion. So we define a distortion measure as a function d that maps pairs x and x hat to penalty values associated to these two x and x hat values. So in other words, the penalty associated to representing x with g of f of x is the distortion corresponding to this value x. When x is a random variable, then g of f of x is also a random variable, and then we take the expectation over the distribution of x, and this will be the average distortion defined like this. We call it capital D, and therefore a general problem is, given a distortion measure, so given a function d, given a probability distribution for x, find the quantization mapping f, so in particular find the decision of the quantization region and the associated representation points, so the reconstruction function, such that the average distortion is minimized. That's the general problem of designing a quantizer for a certain source statistics and a certain distortion measure. So examples are quadratic distortion, very typical, where we use x is a real number, x hat is also a real number, the function d x x hat is simply the square error. And then the distortion is the mean square error associated to the quantizer with the functions f and g. So in this case, we can actually somehow solve this optimal quantizer problem exactly. How does it work? Well, we have two conditions. In fact, it can be shown, and this is something that you can do as a homework. It can be shown that given a set of representation points, so if I fix the representation points, the optimal decision regions are the so-called minimum distance regions or Voronoi regions. So in other words, we associate to the region dq all the x's such that the distance between x and the representation point q is less or equal than the distance between x and any other representation point. So for example, if my alphabet is the plane and I have, for example, representation points like this, the decision regions will be, minimum distance region will be, this will be region 1, this will be another region, this will be another region, this will be another region, okay? So minimum distance regions, okay? So this gives a local optimality condition. Given the representation points, I know how to partition the space into optimal decision regions that minimize the mean square error. But then there is also another condition that says, given decision regions, so if I, on the other hand, fix this decision regions, then the optimal representation points are the conditional means, so the centroids. Let me just explain this, because I know that every time there is an expectation operator, especially if it is a conditional expectation operator, some people get into panic mode. So let's do this properly. We have already seen that in general, if you remember, if I have a certain observation, let's call it y. Oopsie, this is not what I want. Okay, suppose that I have x and y, and I want to find a function x hat of y such that expectation of x minus x hat of y is minimum. The general solution is x hat of y is the conditional mean of x given y given equal to little y. So this is, sorry, I should use here, I want to define it as a function, okay? So this defines a function of y. For every value of little y, this is a value, this is a number, okay? So it's a function of y. So in particular, applying this function to big Y, is a function of a random argument, is also a random variable, and we simply use this notation, okay? So this is something we have already proved using the orthogonality principle. I mean, not prove, I gave you, the explanation of why this is the solution. Now we have the following issue. We have the following thing. I want to find an estimator, let's say x hat of x, given that I know that x belongs to region dq. Okay, so in other words, I could say given that I have another random variable that in this case is fx is equal to q. So, well, I know the answer is just so my x hat of q is going to be expectation of x given fx equal to q. So is expectation of x given x belongs to region q. And how do I write this conditional expectation? Well, the conditional expectation is simply the integral over, well, we know the x belongs to dq, so the integral is necessarily over the region where x belongs to, so it's dq, of a conditional Pdf of x given x belonging in dq, x dx. Okay? But what is this? Well, this is simply the I can get it from the no, when I'm saying this is conditional expectation, I forgot an x here. Yeah, okay. So it's x p of x dx, but of course I have to use the right conditional distribution, right? So what is the conditional Pdf of x given x belonging to a region? So it is simply obtained by taking the Pdf px of x, multiplying it by the indicator function x belongs to the region. But of course, at this point, this does not integrate to 1 because we are restricting the domain of the Pdf to the region D. And then we have to divide by the probability of the conditioning event, which is simply the probability that x belongs to the region. Okay. So, in other words, what is this? And now, what is this probability? Well, this probability is simply integral over dq of px dx. This is the probability that x belongs to the region q, and so the overall thing there is written as the integral over dq of x p x dx. The indicator function is 1 over dx, so, and then divided by the integral over dq of px dx. So somebody of you would immediately recognize this as the so-called centroid of the region dq. So in other words, if this probability density was, for example, a mass density, so we have a region with a certain mass density function, and I say find the centroid, well, you do exactly this. You integrate over the region x times the density divided by the total mass, which is just the integral of the density over the region. So this is the formula for a centroid. What is this? Some left over. Okay, so this is the result, the so-called centroid of the region. So now we have basically two conditions that together form a system of a consistent system. So on one hand, given the representation point x hat, we can determine the optimal region as the minimum distance regions. On the other hand, given the regions, we can determine the optimal x hats as the centroid of the regions. So unfortunately, it's very difficult to come up with a set of regions and centroids that for which the two conditions are consistent. So what people typically do is to do what is called an iterative algorithm. You start with so this is it's called the Lloyd Max algorithm. You start with a set with some points, for example, randomly generated according to some distribution, and those are your initial representation points. Then you determine the minimum distance regions according to an algorithm that, I don't know, is complicated, finds the minimum distance, I don't know, in some sort of space tessellation like this. I'm doing really bad, okay? But you get the idea, okay? Something like that. Then, of course, these red points are not the centroid of this region. So what you can do is to recalculate the points as the centroid of the newly determined regions. This will create a set of slightly different points, maybe, I don't know, these points, right? Then you can recalculate the region for this new set of points, and you keep iterating. And this algorithm converges to a local optimum. So unfortunately, there is no guarantee to convergence to a global optimum in general, especially for high dimensional problems. Instead of 2 dimension or 1 dimension, if you go to n dimension when n is large, you can do this, but of course, the solution generally, the convergence point at the end depends on the initial choice. So you can repeat this for many randomly initialized choices, and at the end find the best quantizer. Okay, so we have no guarantee that the algorithm converges to a global optimum, but at least to a local optimum. So this is a way of designing a quantizer that minimizes the square error distortion, or the mean square error between x and its representation x hat. Okay, so now you can see that designing quantizer is not an easy task in general, right? And in general, we could here I have described a one-dimensional case where we operate on the real line. Then I have drawn some pictures for the two-dimensional case where we operate on the plane. In general, we can operate in n dimensions, so put points in a n-dimensional space where these regions becomes very complicated n-dimensional polytopes. So even just describing them becomes a problem. Then imagine that we are going to take a block of n source symbols, and we want to use, I don't know, k bits. So in total we have 2 to the k points. So our capital Q is 2 to the k. This number may be, I don't know, 100. So 2 to the 100, imagine, is an enormous number. So designing these things by hands with when we work with high dimensions is very, very impractical. So now, as usual, as for channel coding, we have two problems. The problem, sort of design problem, is find efficient algorithms to do quantization. The information theoretic problem is what is the fundamental limit of these multidimensional quantizations. So given a certain source statistics and given a distortion measure, what is the best rate achieving a certain distortion, or the smallest possible distortion for a given rate? And here, by the way, the rate is always the number of bits per source symbol. So in this case, it would be 1 over n times log q. Q is the size of the quantizer. 1 over n is because we want bit per symbols, and this will be the quantization rate, okay, in bit per source symbol. So it's pretty clear that low rate means small q, which means a small number of quantization points, which intuitively from this picture you immediately see large decision regions and therefore large error. So there is a trade-off between distortion and rate. High rate means low distortion. When you, for example, encode an image using JPEG, where you can specify the compression rate. If you want to encode it at 1 bit per pixel, you get a quality. If you want 0.1 bit per pixel, you get a much worse quality. If you want like 3 bit per pixel, you get almost like perfect. So you see immediately that there is a trade-off there. Okay. So the problems, the information theoretic problem setup is that we have a sequence from an IID source. So we have a probability vector here that is our xn distributed according to some probability distribution. And for the moment, we restrict to discrete alphabets. So notice that discrete alphabets, we could encode the source without loss. Because we can compress to the entropy. So of course it makes sense to talk about rate distortion only when we want to encode at rates smaller than the entropy. Smaller than the entropy, then we have to introduce some form of distortion. Then we will generalize this to continuous alphabets, for which basically, well, the source cannot be encoded at the entropy rate because the entropy rate is not defined, and then we necessarily have to introduce some form of distortion. So a lossy source code with block length n and rate r is formed by an encoding mapping that maps source sequences into the indices from 1 to 2 to the nr, and a decoding mapping that maps the indices into representation sequences in an alphabet x hat. We have a distortion measure exactly as before, and simply we define the distortion between two n sequences, x and x hat, as the distortion per symbol. So it's 1 over n, sum of the distortion over the symbols. So this is the n-dimensional generalization of what we have already seen before. You see, it's exactly a quantizer. Simply it works on vectors of length n. Okay? Then we can define the average distortion achieved by this code. In general, this is a function of n because these are, the encoder and decoder operates on blocks of length n. And we say that a pair RD of rate distortion is achievable if there exists a sequence of codes of rate R, an increasing block length n, such that in the limit the achieved distortion is not larger than d. And we call the ray distortion region for a source x and with distortion measure d the closure of all RD achievable pairs. So in general, there will be a trade-off. If we put here the rate, actually the distortion, for example, and the rate here, well, there will be some trade-off region for which all the points here are achievable. So for a given distortion, and then there is a boundary, and then points here are not achievable. So if you want for the given distortion D a rate which is less than this boundary R of D, then such codes do not exist. There is no code, no family of codes achieving in the limit distortion less than D with rate less than R of D. So we define the ray distortion function as precisely the boundary of this ray distortion achievable region. So what the boundary I have I have drawn in this picture. So in other words, R of D is the infimum of all dr for which Rd is achievable. And vice versa, if we flip the role of R and D, we define the distortion rate function is d of r is the inf d such that R and D are achievable. So that's essentially the same function when you exchange the role of R and D. Okay? Good. So we are interested in determining the rate distortion function for a given source and a given distortion measure. And this is the Lossy source coding theorem, which is given by this result. So for discrete memoryless sources, where X is a discrete memoryless source with a certain probability distribution Px over the alphabet calligraphic X, we define a reconstruction alphabet X hat, a distortion measure that maps X and X hat into R plus, according to the above definitions, and the result says the ray distortion function for this problem, R of D, is given by the minimum of the mutual information between X and X hat over all conditional distributions of X hat given X, such that the average distortion constraint is satisfied. Okay? So remember that I want to make a comment here, okay? A comment on the structure of this problem. If you remember, in general, the mutual information between two random variables, jointly distributed random variable, is a function that I call this calligraphic thing, and it is a function of the PDF of one random variable and the conditional Pdf of the second random variable given the first. So in other words, the mutual information is a function of the joint distribution, and therefore it can be seen as the joint distribution is simply the product of these two, and we can look at the individual dependency between of the mutual information with respect to the marginal distribution of one variable and the conditional distribution of the other variable given the one. Okay. Now, if you remember, at the beginning of this course, we have said that this function has a very important characteristic. It is a concave function of Px for fixed transition probability P x hat given x. And it is also a convex function of, in the other direction, say P x hat given x for fixed Px. So it has this concavity convexity property. if you remember, when in the channel capacity problem, the result was the capacity cost function, let me write here, C of B, was the max over all input distributions such that the average cost constraint is satisfied of the mutual information of x, y, and this is a function of px and py given x. Now, in this context, in the context of channel coding, this transition probability is fixed by nature. This is the law of the channel relating the input and the output of the channel. There is nothing you can do about it. And here we optimize with respect to px. And this is a convex problem because we are maximizing a concave function subject to this convex constraint. Now here in the rate distortion problem is almost like the opposite. We are minimizing the mutual information between two variables, but now the source, so nature, fixes px. Px is fixed because this is the probability distribution of the source. There is nothing we can do about it. But what we can do is to choose an appropriate conditional probability of the representation variable x hat given x, so we can actually look at the optimize with respect to this guy, right? And in fact, we can minimize the mutual information because now we want to have a rate which is as small as possible. And this is again a convex problem because now we are minimizing a convex function with respect to the transition probability for fixed marginal probability of x. And also the constraint here is convex. So this is a convex problem. And as you can see, the two problems have a very appealing symmetry. Something is fixed by nature, something we can optimize, and it turns out that we are lucky that we are optimizing. When we want to minimize, the function is convex. When we want to maximize, the function is concave. And the constraint is always convex because this constraint defines a convex set of, in this case, in the case of channel capacity, a convex set of probability distributions over the input, and in the case of rate distortion, a convex set of probability transition matrices between the input and the output. I mean, the output, the representation. Okay. So this is the inner structure of the problem. Now, before proving the theorem, let me give you a couple of examples, because now, okay, believing this formula, now we have a formula to compute the rate distortion function. So for a given source and a given distortion measure, in principle, we can run this optimization and find the rate distortion function. So this is a simple example, the so-called Hamming distortion for a binary source. So imagine that we have a binary source, is a Bernoulli P source. So Bernoulli P means that the source generates zeros and ones independently, and the probability of 1 is P. So we define as a relevant distortion measure the so-called Hamming distortion, which is a distortion measure that gives you 0 when x is equal to x hat, and 1 when x is different from x hat. So it's the number of errors that we make in representing the source. Okay. And the result here is that the rate distortion function for this case is simply the binary entropy of the source, h of p, minus the binary entropy of the distortion d, when d is a number between p and 1 minus p, and is simply 0 when d is larger than the minimum p1 minus p. Okay? So let's explain this result. This is very easy to show, but so we can do as follows. First of all, let's consider the case that P is less than 1/2. Because if P is more than 1/2, then what we can do is just flip all the zeros and the ones, and we go back to the case where P is less than 1/2, encode that source, and then flip again the result at the end. So there is no loss of generality. So in other words, the ones are less probable, are less or equal probable than the zeros. Okay. Then let's think about the following. So let's consider the case where D is greater than P. So we are in this case. I claim that we can represent the source with 0 bits. How do we do this? Well, we simply encode any x for every x in 0, 1 to the n. We just encode fx equal to the all 0 sequence. The all 0 sequence is a known sequence, so it requires no bits because it's already known at the receiver. Right? It's a deterministic sequence. You don't have to specify anything. So we need 0 bits to represent. And now, what is the average number of differences? For any sequence, you know, the Hamming distortion D between xn and the all 0 sequence is simply 1 over n sum over I of every time we have a 1 of xi equal to 1, right? But this converges to P, but P, by assumption, is less than D. So for large n, by the law of large numbers, this empirical mean converges to a number P, which is less than D. So, of course, this means that with probability that tends to 1, you know, I will achieve a distortion P, which is less than D, so I'm fine. So this is like the trivial case. So the non-trivial case is when the distortion is actually less than the probability of 1. So when we are in the case 0, P, D, right, and D is some number, let's say, in this case, 1/2. Okay. No, yeah, what I'm saying, I'm a bit confused. It's exactly the opposite. So when we want to encode with the distortion which is less than P. Okay, sorry about that. Okay. Because then we cannot do so trivially, right? So in this case, we have to be smarter. Of course, I cannot give you a code. Giving you a code would be giving you an optimal Hamming quantizer, which is generally a very difficult problem to do. So let's just prove that the minimum of the mutual information is given by the difference of these two entropies. So we want to study the mutual information between x and x hat, right? And this mutual information can be written as basically the mutual information of well, let's say entropy of x minus the entropy of x given x hat. So the entropy of x is known. The entropy of x is just h of p by definition. X is a binary variable. So now I want to show that this entropy is essentially subject to the fact that x and x hat have the property that the average distortion is D. This entropy cannot be larger than h of D. So in other words, that the minimum is achieved by this h of p minus h of D. So in this case, we don't have many choices, right? Because, well, both x and x hat are binary. So the only possibility when x and x hat are binary is that, you know, is that basically is making x hat equal to x modulo to some independent variable, for example, let's call it, I don't know, z, okay, such that the probability that z is equal to 1 is equal to d, because in this case I have that the expectation of the Hamming distortion of x and x hat, well, this Hamming distortion is 1 when x is different from x hat, which means z equal to 1, and 0 when x is equal to x hat, which means z equal to 0. And so this is simply the probability that z is equal to 1, and therefore this is d. Okay? And if I do so, well, there is no other, when x and x hat are binary, there is no other possibility. You have only, you know, you have only 4 possibilities. The possibility 0, 0, 0, 1, 1, 0, 1, 1. And among all possible distributions that achieve this, this average distortion, this is the one that maximizes the conditional entropy, because it gives you like the maximum possible independence. And in fact, so this means that this entropy is simply, you know, x plus x hat given x hat, but this is entropy of z, which is precisely entropy, binary entropy of d. Okay, so in this case, because there are no other possible joint distribution that do the job, this is the only possibility, and we have that this is also necessarily the minimum. So this explains this formula. Okay. Of course, in general, problems are not so simple. We can have another example. Now we have to do what is called a leap of faith. Leap of faith is more or less the same as we have done for channel coding. We have said, okay, we prove the theorem for discrete memoryless channels, but actually at the end the theorem still works for continuous alphabet channels. And here the same. Here the theorem is stated and proved for discrete memoryless sources, but in fact it works also for continuous alphabet sources. So here is an example where we work with continuous valued sources. So we have the following result, that the rate distortion function for an IID Gaussian source, Gaussian takes values on the reals, so it is a continuous alphabet source with zero mean and variance sigma square under the quadratic distortion, which is the square error that we have already discussed, is given by this function. R of d is equal to 1/2 log of sigma square divided by d when d is less or equal than sigma square, and is 0 when d is larger than sigma square. So again, let's quickly explain this result. So let's first discuss this case, the case where the distortion is larger than the variance of the source. In this case, so for d greater than sigma square, I claim that the encoding fxn equal to all 0 will do the job. How? Well, let's just look at the average distortion. We want to compute 1 over n sum from 1 to n of xi minus 0, right? And the average distortion per symbol, well, this is 1 over n sum from 1 to n of xi. This tends to sigma square, right? Because, again, by the law of large numbers. So sigma square is, by assumption, less than d. So it means that encoding all the source sequences into the all zero sequence gives you already a distortion less than d. So, of course, we can spend 0 bits because the all zero sequence is a deterministic sequence. We don't need to tell anything to the decoder. Okay. So for the case where the distortion is less than the source variance, our problem is to construct reconstruction variable x hat and then that achieves the distortion constraint and analyze the mutual information. So what we can do here is that it's similar to what the same reasoning we have done for the binary channel, but we have to be a little bit careful because here we want to minimize the mean square error. So we know that in general, the condition for minimizing the mean square error is that the error must be orthogonal to the observation. In this case, the observation will be x hat. So we can make this equal to a random variable q, and why not taking q as Gaussian with a given distortion. So this fixes the fact that the expectation of x minus x hat, in this case will be expectation of q square, is d. Okay? And in addition, this gives this sort of decomposition of the source into the sum of x hat plus the error. And it turns out that since the source is Gaussian, and x hat and q must be orthogonal, so they have to be uncorrelated. The only possibility is to choose that x hat to be also Gaussian, and in fact it has to be Gaussian such that eventually the sum of the variances of x hat and q must be the variance of x. So it has to be 0 and then variance sigma square minus d. So now in this way we have restored the right source distribution, because the sum of two uncorrelated and therefore independent Gaussian is Gaussian, and the sum of the variance is the sum of the variances. If we sum d and sigma square minus d, we obtain sigma. So the correct statistics is that the x and x hat are jointly Gaussian, and the difference x minus x hat is Gaussian, and it is independent of x hat. So now we can compute the mutual information as the differential entropy of x minus the differential entropy of x given x hat. But this is so the differential entropy of x minus the differential entropy of x minus x hat given x hat. But this is the differential entropy of x, which is fixed, minus the differential entropy of q, because at this point x minus x hat, we said it is Gaussian and independent of x hat, so the conditioning on x hat goes away, and at this point we have that this is simply 1/2 log 2 pi e sigma square, and this is 1/2 log 2 pi e d, and therefore we obtain the desired formula 1/2 log of sigma squared divided by d. Okay, so these, we have essentially constructed a joint distribution of x and x hat such that the marginal with respect to x is the required source distribution, and the distortion constraint is satisfied with equality. In order to show that this is effectively the minimum of the mutual information, we can do the following. I'm going to change color to outline. So this line is always true. This line is always true. Simply, we can, once we condition with respect to x hat, then the differential entropy is invariant by translation, and therefore we can simply subtract minus x hat from the first argument. Now, what happens is that if we want to show that this is in fact the lower bound, we can write that at this point, eliminating the conditioning with respect to x hat, eliminating conditioning generally increases the differential entropy, and therefore we get a lower bound generally speaking, and then treating these as Gaussian, even if it is not, we know that the Gaussian distribution maximizes differential entropy, and we know that here the second moment is constrained because this has to be less or equal than d by assumption, and therefore we get another lower bound using the Gaussian entropy here, sorry, d. Okay, and now at the end this is fixed because this is the distribution of the source. So we see that this value that we have found here, when the error x minus x hat is q, which is Gaussian and independent of x hat, is in fact basically attains this lower bound and this lower bound with equality. So this is of course, this must be the minimum because it attains a general lower bound with equality. Okay, so this proves that this is in fact the ray distortion function. Great. Okay, so I want to finish this first part by essentially giving you a preview of the proof on purely graphical intuition. You have to recall the covering lemma. What the covering lemma said. Go back to chapter 3, joint typicality, packing lemma, covering lemma. The covering lemma is what we need for the proof of this lossy source coding theorem. So the idea is that we have the source and then we consider long blocks generated by the source. And with high probability, we know that these long sequences are going to be typical. So we have, in fact, the typical set of the source, right? And we know how many sequences are inside the typical set. We know that there are 2 to the n times the entropy of x typical sequences. Now, what we can do is to consider, of course, also the typical set of the sequences x hat. And we know that only a few pairs of typical x and typical x hat are jointly typical with respect to a certain joint distribution. So we fix, in fact, the joint distribution by fixing px is the probability of the source. And then we fix a px hat given x. So this gives px comma x hat. And this is fixed when we fix the choice of this, right? And in addition, how do we choose this conditional distribution of x given x hat? We choose it such that when x and x hat are two jointly typical sequences, by the typical average lemma, the empirical distortion is very close to the actual average distortion, and it is not larger than d. Okay, so now we have these jointly typical sequences, and now what we do is simply pick a few typical x hats and consider their bubbles of jointly typical x given x hat. We know how large are these bubbles. Each of these bubbles is 2 to the n times the conditional entropy. So if we pick these bubbles such that we cover all the typical set, so basically there are no empty spaces, it means that for every typical x, this can be associated to the corresponding jointly typical x hat. Okay, and of course, because these pairs will be jointly typical, also their distortion will be very close to the corresponding average distortion. So at this point, we have basically constructed a sort of multidimensional quantizer that associates to every typical sequence x, associate an index that corresponds to the representation of the associated jointly typical x hat. And there are no empty spaces, so we can basically encode all the typical x's. And how many bubbles we need to cover the whole set? Well, the size of the typical set divided by the size of the bubble, the minimum possible is this ratio. We let we take these things and neglect the epsilons, we find precisely the mutual information. So this is why the mutual information is in fact the rate of this process. It gives how many, the exponent of how many regions we need to cover the whole typical set of the source sequences. So this is the intuition, and in the next part we see the details of the proof.